Now we start by setting up the augmented matrix 2 minus 1 minus 2, 1 with the 0 vector. Now we're just going to solve this. So R1 half, R1 replaces R1, giving us 1, 1 minus 1, 0, minus 1, 1, 0. And then R2 plus R1, replacing R1, gives us 1 minus 1, 0, 0, 0, 0, giving us the equivalent system of equations, A minus B equaling 0, and 0A plus 0B equaling 0. And let V be in the A solution vector. Then V equals AB. Now let's define our free variables and our basic variables. Our basic variable is A, and our free variable is B. Okay? Now, for creating a basis for the kernel, what we're going to do is we're going to take our free variables and let it be free. So let B equal T, which is an element of the real numbers. And then using our equation, we can see that A is going to equal T. Now we're going to update V. So V equals, this implies that V equals T, T, which equals T times the vector 1, 1. So what does this vector 1, 1 represent? Or what does T1, 1 represent? Well, it means if we want to span our solution space equals the span of the vectors 1, 1. Now, those vectors are the coordinate vectors for the null space. So if we take each of these vectors, so if I look at each of these vectors, they represent the null space for the kernel of T, but they're using the coordinates representation for each vectors. So to create something for the, if I want to look at what the kernel of T is, I need to convert these vectors using the basis for alpha. So my V1 represented using alpha is going to be corresponding to this 1, 1 vector. So what will my V equal? My V is going to equal 1 times 2, 1 plus 1 times 1, 2. So V is going to equal 3, 3. Now in our current vector space, this might seem a little bit counterintuitive. Why did I use a basis that wasn't the standard basis, and why do I have to convert? And it'll make a lot more sense as we go further when we're looking at bases that are polynomials or integrals or sorry, not integrals, polynomials, or our matrices, so on and so forth. But this means that our kernel of T is the span of the vector 3, 3. And while these are the same sets, it's just a coincidence. The process we followed, though, will always work as we move forward. So our basis for the kernel of T is the set 3, 3. Or this implies that the nullity of T is equal to 1. And recall that the nullity is the dimension of the kernel. now we're going to bring this down a little bit for our discussion. And now we're going to look at creating a basis for the image of t. Now, to create a basis for the image of t, we're just going to take what we've already done. We have our basic variables and our free variables, okay? And we want to span the column space. So we want to look at what is the span of the vectors 2, -1, and -2, 1. And from our last week's homework assignment, or 2 weeks ago homework assignment, when we looked at the set of vectors and we said we have a set of vectors and we want to make a basis out of these set of vectors, we create a system of equations where we're adding these vectors together. And then any free variable, we remove the vectors that correspond to our free variables, and the resulting set is a basis. Well, when we create that linear system of equations, we get the same system of equations, and we get the same augmented matrix. So our free variable b corresponds to the vector 2, 1. So we just collect our basic variables, or the vectors corresponding to our basic variables, and this is going to equal the span of the set 2, 1, or the span of the set containing the vector 2, 1, as the vector 2, 1 is the vector corresponding to our basic variables. For the homogeneous system of equations, T alpha beta B alpha equaling the 0 vector in beta. Or the homogeneous system of equations, A T V1 beta plus B T V2 beta equaling the 0 vector beta. And recall that this system of equations will produce the same augmented matrix as T alpha beta V alpha equaling the 0 vector beta. So now we have the span of our column spaces, or what's going to be our image. But this here is representing using the coordinates in W. So to calculate our image, what we need to do is we need to convert each of these vectors, and let's make this a little bit clearer. Each of these vectors into what they represent in W. So this is going to be 2 times the vector, and my first vector is 1, 1. So 2 times 1, 1, plus -1 times the second coordinate vector for beta, which is 1, 2. So this is going to be 2, 1, 1 times -1, 1, 2, which equals 2, 2 minus 1, 2, which equals 1, 0. So the image of T is going to equal the span of the vector 1, 0. Which means a basis for the image of T equals the set containing the vector 1, 0. So that's a basis for our image of T is the set containing 1, 0, and the rank of T, or the dimension of the image, is 1. And note that the rank of T plus the nullity T equals 1 plus 1 equals 2, which equals the dimension of V. And for our finite